Hello, my name is Amireza Ramtin. I'm a PhD student at the University of Massachusetts Amherst. Today I'm going to present the problem of selfishness in self-stabilization. I start with an example of wireless sensor networks. These networks are fault-prone. I mean, some faults such as communication loss, memory sharing cache. Besides, the topology is dynamic. This dynamicity can be modeled with transient faults. Uh, and energy efficiency is important. So some techniques such as clustering may help to reduce energy exhaustion. So consider a fault-tolerant clustering approach for this for the network, and a fault happens in a cluster head. It becomes unavailable, but because of the fault-tolerant mechanism, the cluster head again becomes available. But what if these sensors are selfish and they do prefer to not be clustered? How do we deal with this situation? I will continue my presentation starting with explaining the self-stabilization. Then I will define the problem. Next, I will introduce our approaches. And finally, I will give a case study to show the application of our methods. Self-stabilization is a fault tolerance approach for distributed system. A self-stabilizing algorithm consists of two parts. The first part is guard, which when it is true, the second part, which is an action, will be executed. If more than one rule exists in the system, in an agent, one of those will be arbitrarily selected and executed. So a self-stabilizing algorithm has two properties. The first property states that the system, after starting from any arbitrary legitimate configuration and after a finite number of transitions, converge to a legitimate configuration. And the second property states that after entering that legitimate configuration, the system remains in a legitimate configuration unless a transient fault happens. The problem is because of the private goals of the selfish agents. These private goals may cause the selfish agent deviate from the desired behavior of a self-stabilizing algorithm. So we need to find a solution to deal with these deviations. Previously have been some works for the problem of selfishness in self-stabilization, but none of those have considered the problem of deviation during convergence. Now we will show the three deviation types. If there is no deviation, the system starts from an initial point and it converts it to a legitimate configuration. The green circle is the set of legitimate configurations, and the square is the set of all of the configurations. So this first type of deviation is perturbation. Perturbation means after system enters to a legitimate configuration, and some of the agents may prefer to perturb and change the state of the system in the hope that they will profit in another legitimate configuration. The second type is violation. Violation means that during convergence, some of the agents may prefer to not execute their actions. So the system may stop in a legitimate configuration because none of those enabled rules is executed. And the final type, which is very crucial, is the deflection. The deflection means that we will have violation, we will have perturbation. Besides, some of the agents may execute unauthorized actions during convergence. So instead of the system closes and become closer to the legitimate configuration, it may deflect and may stop in another illegitimate configuration that because of the violations. So our goal in this paper is to answer the question that how do we design a self-stabilizing algorithm for a distributed system given that agents may deviate from the algorithm during or after convergence because of their private goals. In this presentation, I will focus on violation. In our violation-tolerant approach, we consider the concept of probabilistic self-realization to assign some probabilities to the rules that the agents may perturb. Uh, we model the self-realizing system with Bayesian stochastic games. The equilibrium concept for Bayesian stochastic games is Bayesian perfect equilibrium. And when we solve the game, we will have some behavior strategies or randomized strategies that they are distributed function on the actions of the game. So we can assign these probabilities to the rules that corresponds to those actions. So, and with the theorem, we prove that under the assumptions that no illegitimate configuration is Nash equilibrium, the convergence is guaranteed with randomizing the rules based on that equilibrium. We continue with the case study of clustering. For clustering, we use maximum independence set. We build a maximum independence set in the network graph of the system. A maximum independence set, or MIS, is a subset of the vertices of a graph where none of those vertices are neighbor, and besides, they cover all of the vertices. The first algorithm that that have been introduced for MIS and that is self-realizing in the is consists of two rules. The first rule says that the agent exits the independent set, so this part is actually the action if it is a cluster head and has a neighboring cluster head. This part was the guard. So the second rule states that the agent enters the independent set if it is not a cluster head and has no neighboring cluster head. The situation that happens in the first rule, we call it conflict, and the situation that happens in the second rule, we call it pending. We will also assume a utility function. A cluster member gets a reward R, and a cluster head gets a reward R minus C. C is the cost of being a cluster head. In our purpose self-realizing algorithm, we assign the probability P to the action of the state transition. This probability is the randomized strategy that we will find based on the solving the equilibrium for the model of the by modeling the system with a Bayesian stochastic game. As you see in this picture, the violation-tolerant self-realizing MIS algorithm has two rules. The first rule is the same as the basic algorithm. The second rule, the difference is that we here say that agent enters the independent set with the probability of P, and I defined what was the P. We will have some experiments, and in our experiments, we have considered to model the system. We considered scale-free connected undirected graphs. Each scenario, we will have different density networks as our scenarios, and we start the configuration with random initial assigning the state of in or out to any agent, and the reward that we have considered is 10 and the cost is 1. And we will compare our VT MIS algorithm with basic MIS and also the state-of-art algorithm TMIS. TMIS is the first self-realizing algorithm for MIS that has the linear time complexity. For the in the first experiment, we compare the fairness of the algorithms. As you see, our VTMIS has the best fairness index and TMIS has the worst. The TMIS is biased based on the agents that have a smaller number of identity or ID, and so it is not fair comparing to the two others. And we also compare the time complexity. To analyze the time complexity, we consider two terms of the number of the moves as the overhead and the number of the rounds as the convergence time. As you see, for the number of the moves, all of the algorithms show a linear behavior, and as you see, both TMIS and VTMIS have very similar results. And in the case of the convergence time or the number of rounds, again, both of TMIS and VTMIS behave in similar manner, and but in both of the cases, the BMIS has the worst time complexity. So, and finally, we compare the performance of our algorithms in the face of deviations. We observe that VTMIS is reliable to all of those violations that we introduced to the system. TMIS also sometimes protect against the violations. The number of deviations that we saw during our experiments were inversely proportional to reliability. Reliability here means that the rate of the convergence to the legitimate configuration. And we also show that we observe that deflections have a very negative effect on the availability of clusters. As a conclusion, we propose three game theoretic approaches for designing self-stabilizing algorithms in the face of selfish agents. We applied our solution methods to the problem of self-stabilizing clustering, and the analysis of the results suggests that our solutions perform well concerning the fairness and ability to deal with selfishness. So thank you for listening.